So ammonia usually used in industry like mining and also battery production because it can extract the heavy metal and also create harmful wastewater. And usually in wastewater we're gonna have like copper ammonia complex that make it difficult to treat. And usually the current method now is not really fully account to this complex. That's why in this study our aim is to improve the detection by using UVVs and also FTIR spectroscopy so that we can develop a better method treatment.
Hello. In the research background, this wastewater, produced in processes like rare earth extraction and battery recycling, is highly toxic due to the stable complexes formed between ammonia and metals like copper, which complicates treatment. Existing methods such as neutralization and sulfide precipitation often fail to address these complexes effectively, posing ecological and health risks. Next, the problem statement highlights that traditional detection techniques, such as ICP or ES, overlook the ammonia metal complexation, limiting the optimization of treatment strategies. Real-time monitoring of these complexes is essential for improving process efficiency and environmental safety. The research objectives are to predict copper-ammonia complex compositions using thermodynamic and quantum chemical models, to develop rapid detection methods using UVs and ATR-FTIR spectroscopy, and to establish a real-time monitoring system through chemometric modeling to enhance wastewater treatment processes.
Heavy metal ammonia wastewater from industry like rare earths and lithium batteries poses serious environmental challenge. Stable complexes such as UNHT42+ dominate in this wastewater, making traditional treatment like neutralization and sulfide precipitation inefficient. Advanced methods like UVVs and FTIR spectroscopy, combined with principal componentization (PCR), offer accurate detection by analyzing the unique spectral nature of these complexes. Despite this advancement, gaps remain. Rapid real-time detection methods are lacking, and the mechanism for breaking these complexes aren't fully understood, limiting treatment optimization. Theories like the HSAV principle and the Jahn-Taylor effect explain their stability, but debates continue about the reliability of this technique in real-world application. Closing this gap is essential for effective wastewater treatment and environmental sustainability.
Okay, so next is Introduction to Metallurgy. For our study, we investigate the behavior of copper ammonia complex in wastewater to understand their properties and optimize wastewater treatment process. So here's how the study was conducted. First is water sampling. We use copper as a representative heavy metal in ammonia complex wastewater. The concentration of copper was fixed at 200 mg per liter, simulating the condition in copper smelting wastewater. Next, the chemical used included copper sulfate pentahydrate and ammonium sulfate, which all of which were of high analytical purity. So this setup allows us to closely mimic real wastewater condition. Next is experimental design. First is complexation analysis. We studied how copper form complex with ammonia with testing a range molar ratio of copper ammonia from 1 to 16 to 1 to 256. And additionally, we investigate how ion like chloride and nitrate influence the result. Next is for spectral analysis. For quantitative analysis, we use UV visible spectrophotometer to record the spectra of our sample in wavelength range of 220 to 800 nm. And next is data processing. So this is to process and analyze the data. So we use advanced computational tools. For example, the Visual Mintech 3.0 for thermodynamic analysis, and the Gaussian 09W for chemical calculation to model copper ammonia interaction. For evaluation metrics, finally, to evaluate the performance of our model, we use three key metrics: R-square, which is the coefficient of determination. This is for measure how closely the prediction values match the actual data. Next is RMSE, which is root mean square error. This is to indicate the difference between the predicted and observed values. And lastly is MAPE, mean absolute percentage error. This is show the prediction error as a percentage. So this metric allow us to assess the accuracy and reliability of the result comprehensively.
Result and discussion of Frege display the UV absorbance spectra of tetraammine coprom 2 ion, showing distinct peak at specific wavelength that correlate with construction. These spectra are the input for the VCR model. Figure 4C demonstrates the output of the UV VCR model with predicted construction closely matching actual construction. The data fit well with the 95% confidence and prediction patch, highlighting the model accuracy and reliability. Next, the UV-VIS PCR model demonstrates excellent prediction accuracy with an R2 value close to 1, along with a low RMSE and minimal residual. It provides detection and quantification limit of 5 mg per liter and 10 mg per liter respectively. Compared to the FDR-PCR model, it's performed better, offering lower error rates and more reliable concentration prediction. Additionally, the UV-VIS PCR model is cost-effective, eco-friendly, and higher efficient for detecting Cooper ammonia complex.
As a conclusion, we know that UV-VIS and also FTIR spectroscopy are very good at helping wastewater treatment and also sustainable for our environment. So that is all from our group. Thank you.